Hey everybody, today we're going to talk a little bit about a phenomenon that comes right along with our discussion of the force on a moving charge in a magnetic field. So what we see here is a magnetic field that is directed into the board. Now you can imagine a giant horseshoe magnet, if you like, one where the North Pole is where you're sitting and the South Pole is on the other side of your screen. The field lines then would be going into the screen as depicted by the big purple X's. To this little picture, I'm going to add a copper wire. Now that copper wire that I just drew in orange is in the field. It's not making the field, but it is in that field. Let's imagine this copper wire is moving. It has a velocity moving it along as shown, but I will depict that velocity as a little vector arrow, and we'll label it is a velocity like so. Well, now we can ask ourselves, if the copper wire is moving in the magnetic field, is there in fact charge moving in the magnetic field? What do you think? Does a copper wire, which does not itself have to be charged, if it's moving in a magnetic field, are there charged particles moving in the magnetic field? Interesting question. Well, if you said yes to that, you'd be absolutely right, because the copper wire is made of copper atoms. Copper atoms are made of electrons, protons, and of course neutrons. Besides the neutrons, the electrons and protons are all charged particles. Now we know from chemistry class and from our discussion of circuits earlier, we know that the electrons are free to move in the copper wire while the protons are kind of stuck in their nuclei. So let's think about what the force on those free to move electrons would be. Give that a moment's thought. Well, if we use our first right-hand rule, we realize the electron, along with the entire wire, is moving towards the top of your screen. So your thumb should be pointed towards the top of the screen. Your fingers should be pointed into the screen. They indicate the direction of the magnetic field. So which way is your palm on your right hand pointed? Well, it's pointed to your left. But is that the direction of the force on the electron? Actually, no. Remember, the right-hand rule speaks to the direction of the force on a positively charged particle. A negatively charged particle, like our electron, will feel a force in the exact opposite direction. So we can depict that force like this. And there's your force on the electron to the left. Well, something interesting happens. All the electrons in this wire feel a force to the left. So, of course, all those electrons are going to get pushed to the left and sort of congregate over on the other side. I'm going to draw that in for you in just a moment. There are your electrons all over on the right. They've all been pushed because of the force that the magnetic field exerts on the moving charged particles, those electrons, as they move towards the top of your screen. Of course, if the electrons move to the right, they've left behind the protons that they were paired with that are now all by themselves on the left. So let's redraw our picture to depict that. Well, those are some pretty gnarly looking protons there, but there they are. Protons on the left, electrons on the right. They've been separated, and now, because this wire with its charged particles are moving through this magnetic field, something has been created that didn't exist before. There is now something present in that wire that was not really present before the wire started moving. What is that? What is that new concept that exists there that did not exist before? Well, it is potential energy. The left, that means they can go from having some kinetic energy. And if they have no kinetic energy, and then later on they have some kinetic energy, some work must have been done, but the work that gets done is done by electrons have potential energy when they're over here on the left side. Potential energy that they previously did not have. And with that potential energy, they now occupy a place that has a different electric potential than the other side. And we know the term we use for a change in electric potential. What do we call that? Well, we know when there's a change in electric potential between two places, we refer to that as the voltage. So by moving, they create a potential difference, they create voltage. Now, that voltage isn't particularly interesting in this circumstance, right? The only way we can get current to flow is to stop the bar from moving. However, what if we instead create a way for the electrons to flow around to where the positive side is while the bar is still moving? They're not going to just spontaneously move right to left. They're feeling a force left to right, and they're kind of stalemated over there on the right edge. However, if we can create a path for them to go to the positive side, then maybe we'll get current. So let's see if we can find a way to draw that path in. Now look what happened there. I drew some wires, and those wires go along the edge of our picture. There's a light bulb right here, by the way. That's our symbol for a light bulb. And they go around to the other side. So now, as the bar moves, we can get current to flow around this loop. The electrons are going to flow counterclockwise, which of course means current, the imaginary flow of positive charge, will flow clockwise. And it can light up that light bulb. So I've shrunken our picture down a bit, and I want us to think about what factors determine the voltage between this side and that side. Remember, that voltage is just like the voltage a battery creates, and it will determine how much current flows clockwise around our picture. So what factors determine how much voltage there is across that gap, the orange moving copper bar? What factors would matter? Well, do you think the size of the B field matters? Well, of course it does, right? If there were no B field, then there would be no force on the charged particles. If there was no force on the charged particles, then no voltage. So B definitely matters. What else matters? How about V? Does V matter? V, of course, the lowercase v, means the velocity of the moving bar. If the bar weren't moving at all, then of course there would be no voltage and therefore no current to flow around our circuit. But there is a V, and the greater that V is, well, the greater the V is, the more force there would be. Right? Remember, force equals QVB. So the greater the V, the more force. The more force, the more electrons get pushed over to this side. And the more electrons that get pushed over to this side, the more potential energy there is in the bar, therefore the greater potential difference between the sides and the greater current that would flow around. There's one other thing that definitely matters. I think it matters if the electrons move a centimeter apart from their protons or they move 10 centimeters apart from their protons. See, it certainly matters, right? If an electron is further away from a proton, it has more potential energy, and therefore there'd be a greater potential difference. So that is expressed as the length of the bar. I'm going to ask you in a separate exercise to look at a worksheet I've got and look through the unit analysis of this. You will find, I hope, that this all turns out to have the units of voltage. Now, in this particular case, it is often referred to as EMF, but I just want you to know EMF and voltage, they are, in our minds, exactly the same thing. For historical reasons, we've used the term EMF. It's not really important to us why, but delta V is the same as EMF, and it equals BLV. And you might have guessed it, there's a sine theta built in there too. Theta is the angle between V and B. In our picture, of course, that's 90 degrees. In any sort of problem you might hope to see, it'll probably also be 90 degrees, but this is the equation for EMF in a situation like this. And when we talk about EMF this way, this concept is called motional EMF. And you'll get some reading about that in your book this week. But this is a pretty important topic that discusses, or lets us discuss, how things in the real world of very practical use work for us. So thanks for watching, and look for the worksheet on this coming up. But have a great day. Take care.